Good morning once again, everybody, and today we are going to simulate operation of the QAM-16 channel with raised square root raised cosine filters and noise. So basically we are going further in our models, and in fact today we are going to try a discrete channel model. Well, actually we already did that last time, but we at least tried to make a simulation look like it is continuous time signal. But today we are going to add noise exactly to samples of the signal, not a continuous function, and it will work all the same. For this practical exercise, we are going to need some additional files, which I have provided here. The second file is just in case you have problems with toolboxes, because in MATLAB it's, I think it's by default present, and in Octave sometimes you might have problems with installing some toolboxes and stuff like that. For example, if I try now help AVGN, it will say that it requires communications package to be loaded. I have it installed, but sometimes it will tell that you don't have it installed. So you can try install it. It's not working. Some problems occur. This happens sometimes for Mac users. So I decided it's better just in case to provide you with these files so you don't have any problems. In case you have this package installed, you can only load it once you start Octave, and then you can use this function even without that additional file. Yes, so
I
it's
have a question.
yes,
This I see the practical task parameters on the new file you put. The new file that you put is the same as the one you used 2 weeks ago, right? Like the
yes,
parameters you will have.
yes. That is correct because we are still going to design similar filter, so it's okay to use the same filter as it was in first task, but the task
Well,
itself will be different.
for example, in my case, that I was basically following your the step by step with you, but with my parameters. So like, do I
Yes.
have everything done already, or?
No, no, it will be different
Okay.
because last time we calculated ourselves this task, and now we are going to use square root raised cosine
Ah,
filter.
okay, thank you.
So basically, as you can see here, yes, what we did last time was this filter calculation. No, not this filter, but uh, this filter calculation. Now we are going to calculate the square root of that filter, and the formula is slightly different. So this is the formula of our square root raised cosine filter, and this was of the simple raised cosine filter, which we used recently, yes. But as I said, we are not going to calculate that formula ourselves. You can use this second function file. It's not really a function, it's just a file to calculate these filter parameters. Yes, in case you hear some noise, it's some dog playing in background. Hopefully they will calm down soon and we can continue.
So
Uh,
the idea will be to use this script, or we also have to use to change parameters of the equation in this script.
yes, so for example, SPS, this is the samples per symbol here, and this is number of samples per symbol here. So in our case, we are just going to replace this with, for example, 11 or 13 or 15 and so on. Yes, the same goes for this number. This is number of symbols. Well, actually, it is double number of the symbols. So in this case, we are going to use the third column. Now, gamma parameter remains as we have some attenuation, and also we have this beta, which in this case is bandwidth factor. Yes, so you can use all these parameters in this script to design the filter. Yes, this link provides additional theoretical background on this filter calculation. So I think I have it open here. Yes, including all the formulas which were used by this script. Yes, so basically you can repeat these steps if you'd like to, and some mathematical background behind these scripts. Yes. But as I said, today we are just going to use this filter to design QAM-16 modulation type transmission of many symbols and to see how it is affected by using one filter, two filters, how it's affected by noise, and so forth. So that's, in short, our task plan for today. So, you need to download these files and place them in directory where you will be working. As I said, I have already this function avgn in Octave, so I don't download it. But in case you have any problems or just want to be sure, you can also download it. But please keep in mind that what I have provided is for Octave. Yes, so in case I open this script, you will see that all the commands are incorrect. It's not a problem. You can actually save it as, yes, you can replace all the, how to say, symbols. Well, let me actually show it to you, how to make it MATLAB compatible, in case you have this problem with MATLAB too. So, lectures, satellite communication, practical, second task. Okay, so I'm going to make replace all for this comment. Yes, because in MATLAB, a valid comment can only be used a percentage symbol like this. This is invalid comment for MATLAB. So in that case, I just find and replace. Yes, replace with this symbol and make replace all. Yes, now it is compatible with MATLAB. So you can use this as a MATLAB too if you replace all the commands with this percentage symbol. But as I said, usually MATLAB has this already in toolboxes provided by some universities. Yes, and unfortunately our university provides MATLAB only for PhD students. So that's why I use Octave, which is similar, yes, and maybe much more affordable for students. So I don't need this file. Okay, so let us start. And let us start with the idea what we are going to do today. So what we want to do is to simulate the operation of quadrature amplitude modulation with 16 signals. Yes, so regular constellation should be already familiar for you from different other courses. Yes, it consists of 16 equidistant signal points. Yes, like this. So we are going to simulate this by generating some random data, for example, 1,000,000 symbols or 100,000 symbols. Then we are going to transmit this data and let it pass through our filter. So basically, this will be our data source. Then we are going to have filter of the root raised cosine filter. Then we are going to have noise. And the second, well, actually here before noise, we are going to make modulation, yes, modulation, then noise, then demodulation, then second filter to compensate for the first filter, and then actually we have this result. And this result should be scattered around this central point. So this way we will have some sort of the clouds of the noisy QAM-16 signal. It's actually quite easy to find similar pictures in Google. Just QAM-16 noise, and well, in images you will find plenty of similar, yes, pictures. And depending on the signal noise strength, these clouds will be greater or smaller, yes. And in fact, the filters will also affect the shape of these clouds. So what we are going to do today is to try and make such simulations from scratch, yes, by using just a simple Octave or MATLAB code. So maybe let us begin with generating this data and obtaining the ideal constellation of the QAM-16 modulation. So for now, we don't work with this script. And I think we will be working with this script in our second pair today, yes? So I'm going to make a new file, going to save it with some name like QAM-16 and start working with this. So currently we don't really need these parameters, but it is quite good idea to input them now. Yes, so in fact I'm going to use also the same parameters from the last time, just so I don't need to type them in. Yes, so I'm going to specify these parameters like this. Similarly, you do so for your parameters. And in addition, we are going to need one more parameter called number of symbols. Because last time we were interested to see the shape of the signal, how it was looking. And for that reason, we were using quite small number of symbols, 15 symbols here. Now, however, we are going to operate in more statistics, yes, to see how noise affects our signal. We need quite large number of symbols. So let us start with 100,000 symbols, and let us specify this number of symbols as a separate variable. So number of data symbols, and capital is going to be 100,000. So much more. Yes, of course, if we would like, we could just use the same symbols, repeat them, but instead we are going to generate them randomly. And in fact, we are now needing not particularly this format, but some other format. Yes, because for quadrature amplitude modulation, we are going to need two values, one for x-axis, real part, yes, of the signal, and one for imaginary part, y-axis, yes. And the step on each axis is 2 units, like this, yes. So, for example, here we're going to have +1, -1, which we already had, and in addition to that, we are going to need also -3, +3, +3, not 4. And the same way it goes for the horizontal axis as well. -3 here, -1, +1, and +3. So this way, if we combine all the possible combinations of +3, +1, -1, and -3, in total, we are going to get 16 possible points, yes, which are actually ideal constellation points, which I was previously marking you before. So we are going to need to generate random numbers accepting only these values, yes? And let us start with doing that for real part of this constellation. So I'm going to hide this for now. And we are going to generate 100,000 random numbers, taking only values of +1, +3, +2, or -1, -3, yes? Actually, in fact, we are also later going to need signal-to-noise ratio of some kind, yes? But I think we can specify it now, yes? Signal-to-noise ratio, for example, 10 decibels, yes? We are going to change it later, but for now, just to leave it into some place where we can find it later easily. So, the first task is going to be, so I'm going to make a section of the code, task 1, generate QAM-16 data as a random process. Random, yes. So we have functions in MATLAB or Octave capable of generating random integer numbers called rand_e. So let's check this function, how it operates. For example, if I generate rand_e, see help on this function, rand_e. So we specify maximum number to be generated. So we generate numbers from 1 to up to this I max and the dimensions of the matrix we want to generate. So for example, if I want to generate numbers from 1 to 10, and in total I want to have a matrix with dimensions 20 by 30, I'm going to type it like this. Yes, and I have the matrix consisting only of numbers from 1 to 10 in random way. Yes. Now we need to do something a little bit different. We want all the numbers to be either plus minus 1 or plus minus 3. So in that case, we are going to need to do some mathematical alternations to these values. So if we look here, we only have 4 possible values, and we need to map these symbols so that, for example, 1 is converted into plus 3, 2 is converted into plus 1, 3 is converted into minus 1, and 4 is converted into minus 3. Yes, so there are multiple ways to do so. We can find some mathematical coefficients to calculate these symbols. For example, if we multiply any of these numbers with 2, so that, for example, we get here 2, 4, 6, and 8, and subtract 5 from these values, then we are going to get here for 2 we are going to get minus 3, for 4 we are going to get minus 1, for 6 plus 1, and for 8 plus 3. That is one of the ways to do so, yes. It's not really mapped the way I want it, it's more like opposite, but we can always add sign minus here and make it like this, plus 5, yes. This way, so minus 2 plus 5, we are going to get the map we want, yes? Some mathematical changes. We can also use table method, yes? So let us first maybe generate our symbols as they are in range from 1 to 4. So that's what we are going to begin with. Data real, yes, random integers, the maximum value is going to be 4, and we are going to generate a single column consisting of n elements. So let's see how it will look like. I'm going to suppress output now so that it doesn't output all the 100,000s. And instead, I'm going to output only first 100 values so that it's not, how to say it, in some long output process, and we don't have to wait much. It is now raw. I wanted a column, so I switch dimensions, yes. Now it is a column, right? So only numbers from 1 to 4 in a random way. So now I'm going to make a table consisting of the elements. So basically some kind of map, yes. Some kind of map representing our ideal constellation. So let us make this map as a square matrix, yes. And let us draw this constellation. So here we have plus 1, here we have plus 3, here we have minus 1, and minus 3, yes. And similarly, it goes to y-axis, yes. And minus 1, minus 3. So we are going to also need imaginary part generated in the same way, yes. So that is x-axis data. And similarly, we are going to generate y-axis data as imaginary part. And I'm going to suppress this output like this. So now, if we, for example, have x equal to +3 and y equal to -1, for example, then we are going to get to this point. Yes. And in fact, we can also make the matrix 4 by 4 matrix, 4 by 4 like this, yes, which will represent each of these points. So here we'll have all these constellation points, and our current, what I have specified here, is going to be this point, yes. So I can simply address the real value of this constellation by simply specifying number of row, which is here it's matching to 4 or no. Well, for example, let's say that 1 matches -1, 4 matches +3. Yes, so -1 then matches here 1. So we are going to wait, no, -1 -1 matches 2. Yes. So we start here 1, 2, 3, 4, and here we have 4, 3, 2, 1. Yes. So basically, this point has matrix coordinations 4 and 2. Yes, which have been generated by this random script. So, and what we are going to put inside this matrix is a complex value. In this particular case, this is going to be +3 minus 1i. Yes, so we can make this QAM-16 map simply by making this matrix. So let us make this matrix then and see for ourselves. Yes. So QAM-16 map is going to be a matrix, square matrix. Yes. Actually, let me return this, where the first row will have fixed value for the y-axis. So basically, we will be talking right now about these points, these 1, 2, 3, and 4 points, and we need to specify the complex value obtained by corresponding coordinates. So the first point is going to have -3x and +3y. We specified here +3i. The second point has -1x value and +3y value. +3y. The third point +1 for x data and +3 for y data. And the last point, accordingly, is going to be +3 x data and +3 y data. Yes, in MATLAB you can specify complex number just simply in this algebraic form by adding this I. Yes, for example, if I run this script now, you can see the matrix of complex values: one value, second value, third value. So no really difficulties with working in complex numbers in MATLAB. Yes, similarly we do so for the rest of the rows. Each row is accordingly specified and divided, separated by semicolon. Yes, so semicolon means that a row ends, and here we start the next row. For the next row, y value will be +1 instead of +3. So I'm going to copy this row and replace each y value by +1. Similarly, next row will have different y value -1, and -1. And the last row, accordingly, has y value -3. So this is our quadrature amplitude modulation map, yes, matrix, which we are going to use to convert these coordinates into signal points, yes. So I'm going to suppress the output of this matrix by semicolon outside of these brackets, yes. So this semicolon actually tells that I don't want to see this matrix in this command line. But in fact, first of all, I want to check if it's okay. So let me see it. Yes, this looks correct. Oh, well, actually, you can decide for yourself. Do you need to show it or not? The only thing that I'm going to make here is the, not in order not to forget, yes, is the assignment logic. So -3 is assigned 1. The -1 is assigned 2. +1 is assigned 3. And +3 is assigned 4 as a command for this matrix, so that later I'm not confused and I can remember what each of these values actually means. Yes, and of course, any of these random numbers, can be converted into binary form as usually. Yes, for example, 1 can be converted as. Wait a minute. We only need 2 bits. Yes, like this. Well, actually, let us start from 0, 0. 2 can be converted like this. 3 can be converted if we use gray mapping like this, and 4 like this. Yes, the gray mapping actually makes sure that neighbor symbols have difference only in 1 bit. Yes, so that's why here I have 1, 1, so that these and these symbols are different with this bit. Yes, and similarly like here. And well, it's always possible to work with binary symbols as well. So, but instead of generating binary data, we at once generate quadrature symbols. Yes. So what we are going to do now is to make transmitted signal like this. Data. So map random integer numbers to QAM-16 map. Yes. So this will produce. I'm sorry. This will produce transmitted signal. So transmitted signal. Currently, we don't have any filter. Any filtering will have to be used before this process. Well, actually, no. After. So we don't make radio modulation. We don't have any carrier signal here, but we do make this quadrature amplitude modulation. So what we are doing right now is the modulation step. So transmitted signal, data transmitted is going to be QAM-16 map. So x-axis is read by real part, data real, and y-axis is read by imaginary part, data imaginary. So I'm going to check out the first 100 values just to see if it works as intended. Out of memory or dimension. Okay, something is wrong here. Let's see. Data real is like this. So if I address QAM-16, for example, I go this, QAM-16 map. I get this point. If I specify an entire vector, for example, 1, 3, 2, 1, 1, 3, 2, 1, again map, it outputs the matrix. it outputs the matrix, whereas what I wanted was the single vector consisting of 4 values. Yes, so now, okay. So that means that I cannot really work like this, and instead I need to separately work with each of these parts and have its own table for each of them. Well, actually, the table is going to be the same. So what is called these levels is called pulse amplitude modulation. So PAM for both x-axis and y-axis. And once we have PAM on each axis, in total they generate quadrature amplitude modulation. Yes. So I'm going to make a PAM table corresponding to this assignment. Yes. And this is going to be PAM4. Yes, levels like this. 1 is assigned -3, 2 is assigned -1, and 3 is assigned +1, and +3 is assigned, and 4 is assigned +3, like this. Yes, we are still going to need this map later for demodulation, so no point in removing it. But transmitted signal is therefore generated by data real part used by as indexes for PAM4 plus PAM4 data imaginary multiplied with 1i. Yes, a complex unit. So now we want this to be a column, so I transpose it like this. Yes, and we have random constellation points assigned in according to the same logic as would these map. Yes, as I said, this map will be used by us later for demodulating, receiving the signal. But right now we did this simply by reading this vector, each value generated randomly by this function. Yes, so basically, let me show it to you how it works. So data real first 10 values, data imaginary first 10 values, and data transmitted also first 10 values. Yes, so I'm going to output them at the same time just to be able to see them. Yes, so as you can see, first two columns are real numbers. So imaginary part is actually zeros. These numbers are generated randomly, and they take values from 1 to 4. Yes, and accordingly, according to our logic here, yes, we have assigned the logical values. So, for example, for the first position, yes, we have x data +3 matches +1, yes, here, and y data also +3. So we get +1 and +1. Next one is we have here 1 matches -3, and here we have 2, which matches -1. So -3 -1i. Yes, so basically we did this conversion in a table form. But as before, as I said, we can also make some mathematical expressions. So what we want to do now is to plot this signal. Yes, to plot this signal, well, right now we are going to need to plot real part and imaginary part by using function plot. We are going to use multiple figures, so at this moment I'm already going to make figure 1. This will be plot QAM-16 ideal signal, right? And well, if we plot this transmitted signal in complex plane, so real part on x-axis, real data transmitted, imaginary part on y-axis, data transmitted, we are going to use red cross symbol. So R stands for color red, X stands for the symbol shape cross. Let us add grid lines on. Let us also have some labels for axis. So X label is going to be real part. Y label is going to be imaginary part. And the title is going to be QAM-16 transmitted signal, TX signal. For example, like this. What is this cleanup? I don't know. I didn't type it. So let's see how this will look like. It takes some time to think for this, but we can clearly see our real quadrature amplitude modulated signal constellation. Yes. So what I don't like about this plot is, first of all, it's being drawn first time quite slowly, yes, and if I increase number of points, it will be slower and slower. For example, 10 millions will ask some time to plot. It's not responding right now, as you can see, which is not really what we should do, because these points are only 16 unique points, only 16 unique combinations of +1, -1, +3, -3, and so forth. It may even now freeze, yes, because of that. So what we are going to do is to actually display the map, what we have calculated here, instead of this real signal, yes. So I'm going to try hold the program. I can't, so I'm going to kill the process. Yes, and then we'll launch Octave again. So I don't see it here, so instead I'm going to kill it like this. And start Octave again. It's not like this. Practical code P2 and the code. So even now, if I will have this many symbols, here I'm going to plot QAM-16 map instead, which are exactly the same symbols. And by running this simulation, this will be plotted much faster, yes? So no problems. But what I don't like is the shape of this constellation. It should be rectangular as a square, but we can clearly see here that this distance is greater than this distance. However, in fact, the distance is the same. Here are 2 units and here are also 2 units. So in order to address this problem, we are going to, how to say it, use additional parameter here called axis square. Axis square. Let me actually return the correct value of 100 values, because we are still going to plot our received signal as it is, yes. And here you can see now that the shape is correct. Yes, we have this distance matching. Okay, so what I'm going to do now is to, in addition to this signal, I'm going to plot well, actually, there is also one more way, but it's okay. We already have this done. But I'm going to plot, in addition to that, our received signal or transmitted signal. So currently it has no noise, so all the received points should perfectly fit to any of these crosses. Yes. So let's see this by plotting additional signal. So this is our ideal signal. And now I'm going to plot QAM-16, well, basically received signal. And as you know, during the transmission, the signal gets attenuated by this gamma factor, right? So, um, so I'm going to make this transmitted signal. I no longer need this, yes. By specifying transmitted signal simply as a gamma multiplied with transmitted signal. Gamma multiplied with data transmitted. So the signal will become weaker, yes, and accordingly this should be seen in plot. In order to draw extra plot on top of this plot, I'm going to use hold function, yes. So I specify hold on, then I specify plot, real part of the data received, imaginary part of the data received, and I'm going to use, for example, green dots to specify these plots, yes, and then I turn hold off. So now it will plot green dots on top of this plot representing received signal values. Well, green maybe not really best color. Let us make blue. It will be easier to see. Yes, as you can clearly see, all the points have reduced their values. So in order to compensate for that, we actually need to divide by gamma, or let us say multiply it with 1 divided by gamma. So basically we need to amplify signal. So okay, amplify will be 1 divided by gamma. Of course, right now it will cancel out each other, but once we have noise, because noise will be added at this step here, noise, and amplification will happen like this. Actually, let us do it. Well, no. Let us do this correctly. First of all, let us specify signal to noise ratio 100. So that means we have almost no noise, yes? And let us use this AVGN function, AVGN, with specified signal to noise ratio, SNR, like this, yes? So currently we generate very, very weak noise, which is almost no noise whatsoever for this attenuated signal. Now we have to calculate this amplification. So transmitted signal, this will be received signal with noise, right? The truth is we have already used this AVGN. However, I restarted Octave, so I need to use help AVGN, this package load command, yes. You need to do that each time you start Octave. So now it will work, yes. And if we see the plot, nothing will really change. However, if we have signal to noise ratio at some different value, you will see noisy signal, right? Like this. So currently what we want to do is to actually put all these points into correct places. Yes, in order for that to happen, we need to amplify our signal. So we need amplification. Amplify signal. Received signal, yes. So we are going to say that transmit received signal is going to be data received multiplied with amplification. So K amplification is 1 divided by gamma. So K amplification. Now it should, the blue points should match red crosses. And if we magnify this, you will see these blue points. In fact, it has some very, very small noise, yes, but this is indistinguishable by naked eye, yes. So we have matching now everything correctly. And accordingly, if we specify higher noise, for example, 10 decibel, we will have Okay, now we cannot really see the red crosses, so that means that we actually need to change the order of drawing the plot. So first we need to draw this plot here, and then we are going to draw on top of those blue points red crosses, like this. So now we can see clearly original signal values and received values being, noisy, yes. What we want to do next is to demodulate the signal, to detect signal, yes. So basically each point, for example, this point or any other, is then accordingly evaluated by distance or metric to all the possible real points, yes? And accordingly, as it's should be clear from intuition, yes, the correct point is assumed to be the closest one, yes? So basically what we are going to do is now to simply round off these points to find the distances and to, how to say, choose the smallest distance, yes? So that will be demodulation. So we are going to now make the demodulator, and then we will calculate the number of errors, yes? So let me draw some portion of this plot. For example, consider we have original signal points here, and we have some received value like this, somewhere here. Well, somewhere here, in fact, yes? So how Demodulator is going to operate? What we want to do is to find the distance between each of the points, each of the 16 points in total, yes? Between distance of these, distance of these, distance of these, distance of these, and all the other. Well, of course, we assume that noise is not too strong, yes? So that means that originally we were sending this symbol, but because of the noise, this symbol has moved a little bit, yes? And naturally, if the noise is not very ridiculously high, this movement, this displacement will not be large, and it still will belong to this sector, to this area of the symbol. Yes, we can mark these symbols, areas, and it should be considered as this symbol during the detection process. But of course, if noise is too high, sometimes situation can happen like this symbol will be converted into something like this, yes, and it will be incorrectly received. That is actually how errors in communications happen, yes. So we can only make some codes that will make error correcting. We'll talk about these codes later, but for now, we are going to use this logic to demodulate the signal. So how we are going to do that? Well, in fact, we are working in complex plane, real part, imaginary part, and each of these points represents a radius vectors. Yes, so basically we can say that here we have radius vector, and here we also have radius vector. So if we subtract these two radius vectors, we are going to get vector of this distance, and therefore all that will remain, we will need to find the absolute value of this vector distance. So what we are going to do is to calculate the difference of the coordinates, so real part minus real part, imaginary part minus imaginary part, and then evaluate the absolute value of this difference vector. So basically, if let us say we have this map signal as a vector, we have received signal Rx data as a vector. We calculate the absolute value, and we will know this displacement amount for each point, yes? So naturally, we are going to choose the minimum displacement, and therefore that will demodulate. So that is the logic behind how we are going to make this demodulated signal, yes? And for that, we are going to need this map, yes? So how to make it better? Let's think. So what we need to do now is to calculate these distances, right? At the same time, we could process real part and imaginary part separately. Yes. Well, let's see example. Let's see some examples. So we have these, let us say, first 10 points data received from 1 to 10, like this. This should be like before adding noise, yes, the real values, transmitted value. So this should be like this. So we need somehow to find this difference, yes. It's quite simple. We calculate the difference. So I'm going to add a third column as absolute value of data Rx minus data Tx, yes. And one more bracket, I believe, yes. So here you can see this distance, and this distance is not quite large, yes, it's small. And clearly the distance between other points will be larger. So what we actually need to do now is to calculate for this point distance to each of 16 original constellation points. So what I'm going to do now is to take this first value, data Rx1, then find the difference for all this map. Yes, so basically data Rx first minus QAM-16 map. And we'll see all these, and also absolute value, of course, absolute value. So as you can see here, these distances are different. And here we can see minimum possible distance. So that means that most probably, it's not guaranteed, but most probably the transmitted signal was assumed to be this point. Yes, instead of all the other points, which are here, 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 or here, yes? So that's how this detection will work. So we find the difference, and then what is left is just to find the minimum possible value. And this minimum possible value, what we need to do is simply read from this QAM-16 map the correct value, yes? So here we had in QAM-16 map, so let me output it as well. QAM-16 map, this value, -1, -3i, yes? And this way we have detected our symbol. What we do then is we compare with original symbol just to see if it is correct, yes? This was original symbol, and in fact it is correct. So we have received the signal correctly despite the noise. So we need now to make this demodulation, right? So here we are going to have demodulated. Well, and for that, we are going to need some way of calculating all the differences, yes? Because if we do it like this, data Rx minus QAM-16 map, it will say incorrect dimensions, yes? So here we have this many dimensions, here we have this many dimensions, and it will not work. So we need to actually replicate this this map, yes, or maybe even convert this into a single vector, yes. So then we will be able to repeat this 16 times, and the vector will be repeated accordingly n times. So what I mean is, for example, if I convert QAM-16 map into a vector like this with this operation. Yes, I can make it a row if I'd like to. Then I'm going to replicate this row 100,000 times to get matrix with dimensions by 16. Then I replicate my data column here 16 times, yes, to also get x16 data, and then I will be able to calculate this difference. So for that, we can use ripmat command in Octave that replicates any vector. So for example, consider I have some x vector from 1 to 10, and I want to replicate this vector 10 times, so that will be 10 by 10 matrix, each row of which would be this data. So for that, I'm going to use ripmat function, specifying original vector and new dimensions, which are going to be not really new dimensions, but number of replications for rows and for columns. So for example, 10 by 1. And as you can see now, this vector has been replicated 10 times in vertical direction. I could similarly do the same thing in other direction. In that case, I'm going to have this vector replicated horizontally. Here you can see first replication, second replication, third replication, and so forth. So for our data, we need to do it horizontally and repeat it 16 times. Yes, so that would be data Rx matrix, rep mat, and data Rx original 1, and we have 16 constellation points, so we are going to need 16 QAM symbols. Yes, like this. So this will be replicated Rx signal matrix. Next, we are going to replicate the constellation map in a similar way. So that will be QAM-16 map matrix ripmat. Here we are going to convert our map into a vector or into a single vector. So basically it's converted like, so let me show you QAM-16 map. By using this operation, it's converted into a single column vector, and the conversion goes like this. So first we have these values here, then we have these values here, then these values. So the priority dimension is vertical. So similarly, I could, for example, this matrix, 16 by 16 matrix, QAM-16 map, yes, address any element. So for example, if I'd like to see this value, it will have indexes, normal indexes, yes, like here 4 and here 3, yes. But at the same time, I could simply address it by using the number 15. Yes, this is this symbol, 3 minus 1i. Because this goes 4 values, this goes extra 4 values, so now we have 8. 4 more values, so now we have 12. And here we go 3 values, so that will be like this. So this can be expressed through these values. So basically, this will be like this 4, yes, 4 minus 1 multiplied by 4, which is number of rows, plus 3, and that will be 15, right? So it's not really a problem right now for us to do manually. I just wanted to show you that actually addressing 15th element here is the same as addressing element QAM-16 map, like 4 and 3. And QAM-16 map 15 will give the same result. We are going to use that later for easier addressing, yes? So That's why we are going to replicate this map, QAM-16 map, converting it into a column and then into a row, and replication will repeat n times with vertical dimension. So that will be replicated QAM-16 constellation matrix. So let us run this code and see what matrix we have as a result. As a result, we have two matrices. Constellation matrix. If I open it, you will see that each column of this matrix, each row of this matrix is, wait a minute, is it? Yes, each row is the same, and each column value is one of these 16 points. So basically, this is one constellation. And this constellation is just repeating each row. Yes, because we have 100,000 of our symbols, and we need this map for each of the symbols to subtract. And at the same time, we have received signals matrix, yes, here, and you can see that it's replicated by columns. So each column is the same. And the idea is quite simple. Then now we can subtract these two matrices once from another. Yes, so basically this minus this, and so forth. So we can find the distance matrix now. Let us do so. So distance matrix is going to be DST matrix, original matrix minus received signal matrix and absolute value of these values. Yes, so absolute. Here we are going to calculate matrix of distances. Let us see how this matrix looks like. So basically, I'm going to open three matrices now. One, received signal, and distance matrix. Okay, so now I need somehow to resize these matrices. And we can now analyze. So we can see clearly that for the first symbol, which was this value, yes, 1.4446 plus 3 something, which actually is quite noisy, as we can see, but nonetheless, we calculate the distance by subtracting this value from each of these original constellation points. And the minimum distance turned out to be this one. So that means that this signal will be received as this point, although in truth it has been transmitted. Well, we don't know what real value was, but well, we'll see if it is correct or not correct. Yes. So how do we do that? So somehow now we need to find minimum value in each of the column, in each of the rows, and not only minimum value itself, but to find in which column it was. So real value was QAM-16, 16th symbol. So basically, let's see, QAM-16 map symbol, which was 3 minus 3i. Yes, and well, 3 minus 3i is wait a minute, not really 16th symbol, it's 13th symbol. How did it go like this? Let me double check. I'm confused a little bit. QAM-16 map. Ah, wait a minute. I did incorrectly transpose. So, as you can see here, we have first number minus 3 plus 3i and the last number 3 minus 3i. Now I do transpose of this matrix to make it a row, and you can see that imaginary part changed. Yes, that is specifics of MATLAB. Yes, in order to avoid this thing, we need to transpose like this, dot transpose. Yes, then it will transpose correctly. This value is first, and this value is last. Yes, that happened because of this inattention error. Yes, from my part. So we need, when you transpose a complex matrix number, you definitely need to do so element by element, because this calculates some mathematical, I don't know how it's named, but some special case of transpose, yes, which is in place for complex number. For real numbers, this is not a problem because imaginary part is 0 anyway, yes, and this doesn't affect anything. But for complex numbers, we need to specifically use this dot transpose notation, not just a simple. So now let us analyze again these results just to see if now everything is correct. So the minimum distance is here, point number 4, which represents this constellation symbol. And accordingly, if I read constellation symbol from map QAM-16 map number 4, I should get -3 -3i, yes? -3 -3i. So it's read correctly. So what we need now is to read for each row of the distance the minimum value and the position where that minimum value is. This is obtained by using function min. So let's see. Help minimum. Yes, so minimum returns minimum value and index of the minimum value for the array x. So let us try it. For example, min val and min index. Yes, by using minimum for distance matrix. So what it did, it found minimum in each of the columns, right? So if we scroll down this column long enough, we will happen to find all of these values, yes? In fact, it also tells us, for example, in row number 75,082, we had this minimum value in first column. So let us search for it, 75,082, yes. Quite a lot. Here's 82. Here it is, that minimum value that was found by this function. However, we wanted to find by columns, not by rows, and for that we need to specify a dimension. Yes, so here we have empty space and then dimension. We need to find in the second dimension, not in the first. So we specify that we want particularly to search for minimums in rows. Now it finds minimum in each row. Yes, actually we can close everything here now and look min val and min index. Distance matrix we need, yes, we do need it, and the min index. Wait a minute, it's not updated. Like this. Yes, so now we can see that, for example, for the first row, we had minimum value of 0.97 in the fourth column here. Yes, for the second row, it was in the ninth column, and so forth. And these numbers, my minimums index, are now what we can use for our constellation map. Yes, for this QAM-16 map. Well, in truth, we need this like a vector. What we can do now is just simply specify that read from this vector Q16 points represented by these indexes. Yes, and accordingly that will produce the received signal. So that is the logic behind how this demodulation is performed. So let us now program this logic. What we need to do is to find these distances, indexes. So indexes and minimum values. We are not really interested in the minimum values themselves. Yes, so to save some memory in the computer, I'm going to say that this result can be skipped. Yes, but we need these indexes by using minimum function for distant matrix and dimension number 2. So that will be find minimum distances for each symbol. Yes. And what we are going to do next is to simply read from constellation map according data points. So next symbol is going, next step is going to be, first of all, we need this Q16 map vector. So QAM-16 map, like this. Actually, well, okay, let it be like this. I was thinking of putting it somewhere here, but here it's in better place, and this is not like a difficult command to execute. So, and then we are going to data demod to read this Q16 vector map vector values according to the indexes we specified. So this is read mean distance points from map, from QAM-16 map. And the idea is that these data demodes should be exactly the same as data transmitted. Yes, so let's see and try compare it. Yes, so data demode first 20 values and data transmitted first 20 values. Yes, as we can see, the detection performed correctly. However, because of the noise and statistical properties of the noise, it is still possible that because of the noise, some points, for example, as these, were just too far away from original place, and they happen to be in the area of the other symbols, which in that case would be considered as the second symbol. Not second, but fifth symbol here, yes, rather than first. However, they may be originally where this. These are errors during the transmission which happen because of the noise, which is thing we can somehow fight, affect, but at any rate, if the noise is just too strong, these errors will be much more. So what we are going to do now is to actually, we don't want to look through 100,000 of symbols by our eyes. We want to let computer calculate any mismatched symbols, yes? So what we are going to do is to tell him, the computer, count number of errors. Number of errors. By simply comparing data demode, well, let us make it shorter, data dem, with data transmitted. Yes, so if they are not equal, it will produce 1. And what we need to do is then, so basically here, they are equal, so it will be logic result 0, equal 0, equal 0. Assume we have somewhere here error, so it will produce 1. Somewhere here we have error, it will produce 1, and so forth. So once we have this vector of zeros and ones, all we need to do is just to add up together all the values as a sum. Yes, and we will have number of these ones, therefore number of the errors in our simulation. So what we are going to do is to calculate sum here and say that this will be per error, which we want to output to the console. And we can see that from n of 100,000 symbols, we actually did have 1,100 incorrect symbols received. Yes, if we reduce signal to noise, for example, to 5 decibel, then the noise should be stronger and we should have more errors. Let us check this fact. Yes, indeed, we have more errors, and you can clearly see here that the data points are mixing. Yes, it's difficult to detect it correctly. And at the same time, if we have signal to noise ratio 100 decibel, that means we have almost no noise, and we should get strictly 0 number of errors, which is correct. Yes, so the first part of our simulation works correctly. We haven't added any filters yet, but we now have the program capable of simulating the quadrature amplitude signal modulation with noise in channel without any band limited effects. Yes, so next step, we are going to add a filter after a short break of 17 minutes. So let us continue at 9:40. Today we are probably going to have only 2 lectures because I think we will be able to complete our practical exercise in this second part. So we'll start with questions at 9:40, but if you have some short questions, you can ask now. Okay, then I'm
Maybe
going.
you can just please leave the script maximized.
No problem. Of course, I can leave it on. So this part probably you don't need much. Yes, so I'm going to scroll it like this. Yes. Here we have also plots. Well, I'm going to make it slightly smaller, yes, like this. Okay, so. Can I make it fit everything? Okay, I'm going to just remove some white space so that you can see that SNR is currently 100. Okay, so see you then in 15 minutes at 9:40. Thank you, and let's continue later.